Before we talk about rational numbers and classifying rational numbers, we do have to set some groundwork first. First thing we want to look at is 6.2e, which says I can extend representations for division to include fraction notation, such as a over b represents the same number as a divided by b, where b is not equal to 0. Basically what this is saying is that whatever number a over b is the same thing as a divided by b, and the only exception to that is b cannot be equal to 0. And why is that? Well, because I cannot have 0 as a denominator in a fraction. So you can never have any number over 0. Like I could not have 5 over 0 or 100 over 0. And if you really want to know why, we'll talk about that later on. But just know for now, we can't have a number over 0. All right, so let's take an example of 1/3. Now we know what 1/3 is. We've dealt with fractions before. And so we can have one whole of whatever it is, one whole item, cut it into 3 pieces, and we have 1 piece, right? So this is how many pieces we've cut it into, and this is how many pieces we have. And so we have 1 out of 3. That's another way that we could say this, is that our fraction bar could actually mean out of. So 1 out of 3. Now, what this teak is trying to tell us is that really it's the same thing as 1 divided by 3. And if we think about that, well, we had 1 whole, and we cut it into 3 pieces. So it is 1 divided by 3, and we get 1/3. So 1/3 and 1 out of 3 and 1 divided by 3 are all the same thing. Another example that we can look at would be 1/2. If I have the fraction 1/2, that's 1 out of 2, or I could say I have 1 divided by 2. And so whatever my one object is, I can just cut it into 2 pieces, and I have 1 divided by 2, or 1/2. Or we could say we have a pizza, and we want to share that pizza evenly between 2 people. So if I have 1 out of 2, or 1 pizza divided by 2 people, each person gets 1/2. So 1 divided by 2 and 1/2 are the same thing. So now that I understand that, we can explore this concept a little bit more. Now, we all know, because we're fraction experts, 4/4 is the same thing as 4 out of 4, or if I have an item that's cut into 4 pieces and I have all 4 pieces, then I have the whole thing. So 4 over 4, 4/4 is the same as 1 whole. Well, that's the same concept here as 4 divided by 4, which we also know is 1. So a number divided by itself is going to give you 1. The pattern does hold true. Well, then what if I had 9/3? I had this improper fraction. Well, we have a few different ways that we can look at it. There's 9/3. Well, if I have 9/3, then I have 1, 2, 3 whole objects. So my answer would be 3, or my simplifying that would be 3. Another thing that I could do is I could say, well, I have 3 groups, and I'm dividing up 9 objects, or have 9/3, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 3 in each group. So 9/3 is 3. Or I could say 9 divided by 3 is 3. So 9/3 and 9 divided by 3 are the same thing. So what 6.2e is saying is that any fraction, a over b, is the same thing as just a divided by b. Whatever the number a is, divided by whatever the number b is. 9 over 3 is just 9 divided by 3. Well, that makes it really easy to do some other bigger numbers. What if I had 24/4? Well, 24/4, I don't have to sit there and draw out models and figure that out. I know that 24 divided by 4 is going to be 6. Or if I had 100/4, that would take a really long time to draw that model, but 100 divided by 4 is 25. And I know that because a dollar divided into 4 equal sections is 25 cents, right? So 100 divided by 4 is 25. And then if I had, say, 64 over 8, I know that would simplify as 64 divided by 8, which is 8. Alright, so we also need to look at Venn diagrams as well. So here I have a couple of Venn diagrams. Now, over here on the left, this is typically when you think of Venn diagram, this is what you think of. Two circles that overlap, and Venn diagrams are used to show the relationship between different groups of items. So here I have students as one group and boys as another group. And so I could have, say, Luke. Well, Luke is a student and Luke is a boy. So Luke would fall into this category as both a student and a boy. But maybe I have Daisy. Well, Daisy is not a boy, but Daisy is a student. So Daisy would fit into this category here, or this group here. Daisy is a student. Daisy is not a boy. Or we could have Mr. Ermintz. Mr. Ermintz is a boy, but Mr. Ermintz is not a student. And so Mr. Ermintz would fit into this category here if we were to classify the students in our classroom, for example. And here on the right side, here's another Venn diagram. Very similar. I have three different categories, though. So I have student council, choir, and UIL. So perhaps you're a student, you're in student council, and you're in choir, then you would fit into this category here. Or if you're only in choir, not in UIL or not in student council, then we would put you here. If you're in UIL only, then down here. Student council only would be here. If you're in choir and UIL, then we could put you in this area here. Or if you're in student council and UIL. But what if you're a really busy student and you do all three, student council, choir, and UIL, then you would fall into this area here where you're a member of all three groups. Let's look at a really complicated Venn diagram. So this has 5 different groups. Now, you're never going to have to deal with, as far as in public school, probably ever have to deal with a Venn diagram this complicated, but we have 5 different groups, group A, B, C, D, and E, and if you're a member of all 5 groups, then you're right here in this middle section. But maybe you're only a member of groups A and B, well then you would be here. Only a member of group C, only a member of group B, C, and D, and so on. So it shows a lot of different possibilities when looking at relationships between different types of groups. And so this is a very complicated Venn diagram, but it is still a Venn diagram. I want to look at a couple more here. These are what's called nesting Venn diagrams. So this has to deal with groups within groups. And so maybe over here I have students in our class, and in this group maybe I have girls. So I could put all the girls into this group here. Daisy, for example, would fit here into this one, or Sally, or whomever, right? So they would fit into this group here. But notice that Daisy is not only a girl, but Daisy is also a student. All of the girls, all of circle B, or group B, all of this group fits inside of group A, meaning that all of the girls in our class are students. However, Luke would be out here. So Luke is a student, but Luke is not a girl. All of the students would fit into this whole bigger circle, but girls would be a smaller group within a group. And so later on we'll talk about this. We'll call them sets and subsets. But for now, you just have to realize that this is just a group within a group. So all of the girls in our class are students, but not all of the students are girls. And I'll say that again. I know that's a little bit confusing, but all of the girls in our class are students, but not all of the students are girls. Case in point, Luke is a student. Luke is not a girl. So after school, I'm going to call my mom and tell her, Mom, can you come pick me up? And of course she says, yeah, absolutely. Where are you? And I said, well, Mom, I'm in Texas. Okay, well, that's pretty large. Can you be more specific? Can you tell me more specific where you are besides just Texas? Oh, you know what, Mom, I'm sorry, you're right. I'm actually in Pearland. Can you come pick me up in Pearland? Okay, that's better, but that's still pretty large. Can you be even more specific? Yes, Mom, I can. Can you come pick me up at Wilder? And so here I have a nesting Venn diagram with 3 different groups. Notice that all of Wilder, doesn't matter where I go within Wilder, I am in Pearland. No matter where I go in Pearland, I'm still in Texas. So all of Wilder is in Pearland. All of Pearland is in Texas. Now also notice no matter where I go in Wilder, I'm still in Texas. So all of Wilder is also in Texas. So these are showing the relationships of these sets and subsets, or the groups within a group. And so all of Wilder is part of Pearland. All of Wilder and Pearland are part of Texas. So that's important to know. Now, I could also say maybe, we have Earth, and Earth is in our solar system, and our solar system is part of the Milky Way galaxy. We could explore this or explain these relationships using several different options. Now we need to talk about a few types of numbers. First type of number that we need to talk about is our counting numbers. Our counting numbers, when we were pre-K or kindergarten for some of us, or even before pre-K for a lot of us, we started to learn to count. And when you learn to count, the first number that you learned, of course, was 1. And then 2, 3, 4, 5, 6, and so on, right? So you learn to count. Those are your counting numbers. Now in 7th grade, we call those natural numbers. They rename it so you feel fancy about yourself. But that's just our counting numbers. So those are the numbers that we learn when we learn to count. Well, they take our counting numbers and they expanded upon that, and they call these whole numbers. Now our whole numbers are 1, 2, 3, 4, 5, and so on. But there's another special number that they add to consider our whole numbers. Our whole numbers are our counting numbers and 0. 0 is a whole number. That's important. Integers. Integers are our whole numbers and their opposites. So all of our whole numbers are integers and their opposites. Well, what does opposites mean? So over here I have a number line, and in the middle of my number line I'm going to put the number 0. Number 0 is a whole number. And then I just have some numbers. So let's say I have 1, and it's not to scale. Maybe I have 10 or 100, right? Or just whatever my numbers, whatever I want them to be. On the opposite side of 0 on my number line. So over here, I have 1. On the opposite side of my number line, on the opposite side of 0, I have -1. On the opposite side of 10, I would have -10, and on the opposite side of 100, I would have -100. And that would go for any number. So opposite of 75, -75, right? So it's just the opposite side of a number line. If I were to take my number line and fold it in half, 1 and -1 would match up, 10 and -10, 100, -100, those numbers would match up. And so those are opposite numbers. So any whole number is an integer, and any opposite whole number is also an integer. So that's an important distinction there. So whole numbers and opposites. Now for rational numbers, I always circle ratio. And I circle ratio. Now ratios we'll talk about later on in Unit 8. But ratios, Mr. Ermitz's favorite way of expressing a ratio is using a fraction. And so here I have a fraction. It's a 2-to-4 ratio, but I'm going to express it as a fraction. Ratios behave like fractions, or can behave like fractions, and so we'll worry about that later. Just know that the only reason I talk about that is so that way I can understand that a ratio, or be reminded that a rational number can be expressed as a fraction, ratio, right? It can be expressed as a fraction or as a decimal. So 2/4. Well, I also know that 2/4 is the same as 1/2. So 1/2 is a rational number. It's a fraction. Or I could say that half of a dollar, 50 cents, or 50 hundredths, if you will, that is also a rational number. So a rational number is any number that can be expressed or written as a fraction or a decimal. Obviously, 1/2 can be written as a fraction, or even here, half a dollar written as a decimal. So those are rational numbers. But let's look at number 5, for example. Is 5 a rational number? Can I write 5 as a decimal or as a fraction? Well, if that was $5, could I say that's the same as $5? Are these numbers the same? Did it change? Did my value change? Which one of these numbers is bigger? And of course, they're the same thing. $5 is the same as $5. The only difference is the way that I wrote the information down. So I wrote a decimal 00, but it's the same thing. So here I have the number 5 written as a whole number and then also written as a decimal. So 5 is, in fact, a rational number because I can write it as a decimal. Can I write 5 as a fraction? 5 over 1. Well, that's the same as 5 divided by 1. And 5 divided by 1 is 5. So here I wrote 5 as a decimal. Here I wrote 5 as a fraction. So 5 is a rational number because it can be written as a fraction or a decimal. What about 13? Is 13 a rational number? Sure. There's 13 as a decimal. Here is 13 as a fraction. 13 divided by 1, right? So these numbers are rational numbers. All right, so I'm going to show you an example in just a moment. And then what I want you to do after the example is I'm going to have you pause the video, redraw this Venn diagram, this nesting Venn diagram on your paper, and then I want you to classify each of these numbers into its best spot. All right, we'll do one together. So 5. We talked about 5 just a moment ago. We said that 5 could be written as a decimal. We also said that 5 could be written as a fraction, 5 divided by 1, which is 5. So 5 would then be a rational number, right? Sure, it is. But again, remember my example, Mom, can you come pick me up? Where are you? I'm in Texas. We can be more specific than that. So, Mom, can you pick me up? Sure, where are you? Well, I'm at Wilder. So, is 5 an integer? Well, integers are whole numbers and opposite whole numbers. So, yeah, 5 is an integer, but is that the best classification? No, we can be more specific. Is 5 a whole number? Yes, it is. Mom, can you come pick me up? Where are you? I'm at Wilder. Of course, I'll be there soon. Here I have 5 as a whole number. That's my best, most specific classification. So I want you to go ahead and pause the video and classify each of the remaining numbers where they go. Alright, so how do you feel about that? Hopefully good and confident, but let's see. So the next number, 100. Where would 100 go? Well, I could write it as a decimal or a fraction, but I can be more specific. Can I put 100 as an integer? Well, integers are whole numbers and opposite whole numbers, so sure it would fit, but can I be more specific? Is 100 a whole number? Yes, it is. So 100 would fit here in whole numbers. How about -3? Is -3 a whole number? No, it's not. So let's see, can I be as specific? And if not, I'll work my way out. Well, -3 is not a whole number. So is -3 an integer? Well, 3 is a whole number. -3 is opposite whole number. So yes, integers are whole numbers and opposites. So -3 would be an integer. 21 2/10. Is that a whole number? No, got that 2/10 there. So it's not a whole number. Well, it can't be an integer if it's not a whole number because it has to be a whole number or the opposite whole number. So the best I can do is going to be a rational number. So 21 2/10 is rational. 17, oh, that's easy. 17 is a whole number. Ooh, look at this one. -5 over 1. Well, 5 divided by 1 is just 5, right? So -5 over 1 is just -5. So I would simplify that to -5. -5 can't be whole because of that negative. So best category would be integers. 4 over 4, did you put that as a rational? I mean, it is, right? But 4 divided by 4 is 1. Ooh, look at that. So I could put this number here. Oh, I didn't finish writing that one. So I could put 4/4 as a whole number because 4 divided by 4 is 1. What about -12? -12 would be an integer because it's negative, so it can't be a whole number. 1/2. 1/2 is not a whole. If I have half of something, I don't have the whole thing. Well, if it's not a whole number or the opposite whole number, it's not integers. So the best I can do is to put that as a rational fraction or decimal. What about -9/3? 9 divided by 3? 3, but this is negative. So negative 3, that would, oh, yeah, I already have one here in integers. So negative 9/3 is an integer. 8/2. Did you put that one as rational also? I know some of us did, but 8 divided by 2 is simply 4. 4 is a whole number. So 8/2 would be a whole number. 75 hundredths or 75 cents, is that a whole dollar? No, of course not. Is it a whole or opposite whole? No. So 75 hundredths is going to be a rational number. 100%. If I have 100% of something, how much of it do I have? I have all of it, right? So 100% of something is one whole of whatever that item is. 100% I would put as a whole number. Well, then what about 50%? Where do you think that would go? 50% is half of something, right? If I have 50% of something, I have half of it. So 1/2, oh yeah, I already know that the best thing I can do with that is a rational number. So 50% would be rational. And there we go. That's what we need to know for classifying numbers. If you have questions, please ask me in class or through email or the appropriate help channel online.